When you think about the phrase Silicon Valley, what is the very first image that actually pops into your head?
Oh, probably something incredibly sleek, right?
Yeah, if you're anything like me, you're probably picturing endless scrolling lines of code.
Yeah, or maybe theoretical physicists writing complex algorithms on those giant glass whiteboards.
Exactly. Or just incredibly minimalist software interfaces. It all feels very ethereal.
Sure, it feels weightless, almost invisible.
Invisible, yes. But today, we are taking a deep dive into something completely different. We are looking at the gritty, heavy, deeply physical foundation of the digital age.
Which is so important because it is remarkably easy to forget that the cloud is actually on the ground.
It is on the ground.
Yeah, everything digital requires a physical reality to exist. The software you use every day, it lives on physical servers. It's transmitted through physical cables, processed by physical chips, and that physical reality, it had to be built by someone using raw materials.
And that is exactly the mission of today's deep dive. We're going through a stack of sources today. Specifically, we're looking at these articles titled The Architect of the Silicon Forge and The Architect of the Silicon Valley Factory Floor.
Great titles, by the way.
Really great titles. And the goal here is to explore how sheer theoretical genius, how it actually becomes a tangible physical reality.
Because theory is just theory until you can make it.
Exactly. So we're going to uncover the story of this unsung hero named Julius Blank. And he is widely considered the man who built the factory floor that made Silicon Valley possible.
Yeah, and I love this story because history has a habit of overlooking the pragmatists in favor of the theorists.
Perhaps.
We love the narrative of the eureka moment, right? The brilliant concept scrawled on a napkin at a diner.
The genius in the garage.
But a concept, however brilliant it is, cannot change the world until it is reliably manufactured.
I actually want to frame this with an analogy just to set the stage for the listener about the scale of the problem we're looking at here.
Okay, let's hear it.
Imagine someone like an absolute culinary genius writes the most brilliant, world-changing recipe in human history. A recipe that is going to feed billions of people. But before they can actually cook this recipe, they realize they have to invent the oven.
Oh, wow. Yeah.
They have to forge the pots. They have to hammer out the pans from raw iron completely from scratch because literally none of those cooking tools exist anywhere on Earth.
That framing captures the bottleneck of the late 1950s perfectly, honestly.
Yeah.
Because the recipe for modern computing, it was just being written by some of the greatest minds of the century.
But the kitchen was entirely empty.
Completely empty, yes.
So to understand why inventing those pots and pans of computing was desperately necessary, we have to look at a massive industry-shaking disruption that occurred in 1957, which brings us to the era of the legendary Traitorous Eight.
Oh, man. Such a foundational moment in tech history.
It really is.
So in 1957, you have this group of incredibly brilliant scientists and engineers, and they grew utterly frustrated with the erratic management style at Shockley Semiconductor.
William Shockley was notoriously difficult to work for.
Unbearable by most accounts. So they defected. They just walked out en masse to co-found a new company.
Which became Fairchild Semiconductor.
Exactly. And this specific defection essentially triggered the birth of Silicon Valley as an ecosystem of startups. It established that whole culture of leaving a dominant company to build something new.
In the middle of this legendary group of defectors is Julius Blank.
Yeah.
And his background is what makes him stand out so sharply in our sources. He was born in 1925 in New York City.
Okay.
But the detail that dictates the rest of this whole story is his training, because amidst a group of world-renowned physicists and electrical engineers, Julius Blank was trained as a mechanical engineer.
And you really have to think about the composition of that room on the day they founded Fairchild.
Oh, yeah. Picture the room.
You have these visionaries who deeply understand quantum mechanics. They can mathematically visualize the flow of electrons through semiconductor materials.
Which is mind-bending stuff.
It is. And they're operating entirely in the realm of the invisible, the theoretical, the electrical. And then you have Julius Blank.
Yeah.
And his expertise is in torque, heat transfer, structural integrity, and metallurgy.
It's like having a room full of brilliant symphony composers and one master carpenter.
That is a great way to put it.
The composers can hear the music in their heads, but someone has to physically carve the violins out of wood.
Exactly. Because if we look at the reality of their situation in 1957, the rest of the Traitorous Eight, they had these world-changing theoretical ideas for new types of transistors.
They knew exactly what they wanted the silicon to do electrically.
But when they defected and they opened the doors at this empty building that was going to become Fairchild Semiconductor, they faced a really stark physical reality.
Which was what?
They had absolutely no way to mass produce their ideas.
I'm trying to picture the timeline and logistics here because if Fairchild is a startup, they are on a ticking clock.
Oh, definitely. They need to make money.
They need to produce something to sell. So couldn't they just, I don't know, cobble together industrial equipment from other manufacturing sectors? Did an industrial supply catalog for this kind of microscopic work even exist?
It did not.
Ow.
At all.
Really?
Nothing. There were no off-the-shelf machines for making semiconductors at a commercial scale. If you wanted a machine to manipulate silicon with microscopic precision, you had to conceptualize it yourself.
Wow.
You had to draft the blueprints and literally cut it out of raw metal yourself.
That's insane.
Blank was tasked with looking at a physicist's mathematical equation, right?
Sure.
And then figuring out how to build a multi-ton machine that could replicate that math in the physical world.
Transitioning from a theoretical idea on a chalkboard to a functioning physical factory is a massive leap.
A monumental leap.
Let's look at the specific problems Blank had to solve, because this is where it gets wild. One of the sources mentions another Fairchild pioneer, Gene Horney.
Yes, Horney.
And he invented something called the planar process. Now, on paper, our sources hail this as the breakthrough that basically makes all modern microchips possible.
Oh, it fundamentally changed computing. But to understand why it was such a mechanical nightmare to build, we really have to look at how early transistors were made.
Okay, set the scene for us.
So, before Horney's invention, transistors looked like tiny, fragile little mountains sitting on a chip.
Like actual bumps on the surface.
And the electrical junctions were completely exposed.
Meaning they were vulnerable to literally everything.
Everything. A speck of dust, a slight vibration in the room, a change in humidity, literally any of it could ruin the transistor.
Which I imagine made mass production pretty much impossible.
We made it incredibly inefficient because the failure rate was just so high. You threw away most of what you made.
Yikes. Okay.
So Horney figured out a theoretical way to manufacture these transistors flat.
Oh, I see. Planar, like a plane.
Exactly. Embedding them flush into the surface of the silicon crystal itself and protecting those delicate junctions under a layer of oxide. He essentially said, instead of building fragile mountains, let's pave a flat, protected road.
Okay, so Horney has this elegant mathematical theory on a chalkboard. But looking at the math doesn't magically pave the road.
No, it certainly doesn't.
Someone has to figure out how to physically force the silicon to do this.
And that is where Blank comes in. His role at Fairchild was entirely about this translation. He had to take Horney's flat road theory and force it into a physical manufacturing reality. He had to design and physically build the laboratory equipment and the manufacturing tools completely from scratch, just to make this process repeatable at a commercial scale.
Wait, let me unpack this for a second. Because he didn't just design the microchips, he had to invent the machine that makes the machine.
He had to invent the machine that makes the machine, yes.
That is just, wow. Okay, the sources mention he had to build fusion furnaces, which, if you don't know the context, that just sounds like he bought a really hot industrial oven. I'm assuming it wasn't quite that simple.
Not at all simple. Think about the chemistry of what they were trying to achieve here. To make the planar process work, they needed to bake specific chemical impurities into a silicon wafer.
Okay.
And this permanently changes its electrical properties. But if the temperature in that furnace fluctuates by even a fraction of a degree,
oh no,
or if there is the slightest microscopic contaminant inside the heating chamber, the entire batch of silicon is ruined.
And we have to remember, this is 1957. He doesn't have digital thermostats.
No.
He doesn't have modern computer-controlled sensors regulating the heat in these things.
No, he had to figure out how to maintain an incredibly precise, uniform heat profile across a quartz tube using purely mechanical and analog controls.
That sounds impossible.
It was incredibly difficult. He was dealing with thermal expansion, insulation, vacuum seals. It was honestly more akin to precision glass blowing in a vacuum than traditional factory engineering.
Because the physicists knew the exact temperature required to alter the silicon, but they didn't know how to build the oven.
Exactly. Blank had to figure out how to force steel and quartz to hold that exact temperature for hours without cracking or fluctuating.
Which perfectly illustrates why they desperately needed a mechanical engineer in that room.
Absolutely.
The theoretical physics only gets you to the starting line. But that was just the oven. The sources also mention he designed their photolithography equipment.
Yeah, so photolithography is essentially the process of using light to print circuit patterns onto the silicon.
But again, we were talking about unimaginably tiny microscopic patterns. You can't just use a stencil and a paintbrush here.
Oh no, you need complex optics. You need lenses that can focus light with zero distortion. And you need a mechanical alignment system that can hold a silicon wafer perfectly still down to the micrometer while the light exposes the pattern.
So Blank is designing all of this too.
Yes. Blank had to design the mechanical rigs that held and moved these lenses and wafers. Think about it. A single millimeter of vibration from, say, a passing delivery truck outside the building.
Oh, wow. It would ruin the microscopic alignment.
It would completely ruin it. So he had to engineer vibration dampening into the physical structure of the machines themselves.
Okay, so you bake the silicon, and once you print on it, you still have to move it around the factory. And silicon wafers are notoriously brittle, right?
Very brittle.
And if a human hand even touches them, the natural oils from the skin ruin the microscopic circuitry.
Which brings us to the wafer handling systems that Blank had to design.
He did those too.
He did. He had to invent the mechanical infrastructure to move these fragile disks through a gauntlet of toxic chemicals, optical alignment rigs, and extreme heat.
Because they can't be touched.
Exactly. They needed to be handled, washed, baked, and packaged, ideally completely untouched by human hands.
So he's essentially designing early robotics.
Pretty much. He was designing robotic handling and conveyor systems when most of this technology had never existed before in human history.
Taking a step back, the scope of his work at Fairchild is just staggering.
It's unbelievable.
Because he isn't just solving a localized problem so his buddies can sell a few transistors, by inventing the diffusion furnaces, the optical alignment rigs, the wafer handling systems. He is inventing the actual machinery that allows the digital age to be mass produced.
He essentially invented the entire semiconductor manufacturing equipment industry single-handedly.
Wow.
It's not an exaggeration to call him the architect of the silicon forge. When we talk about the rapid advancement of technology, things like Moore's law, the continuous shrinking of microchips.
A massive explosion of computing power over the last 60 years.
Exactly. None of that happens without the physical infrastructure to manufacture it. Blank proved that theoretical physics could be reliably, consistently mechanized.
And this is where the story of Julius Blank takes a really fascinating turn, I think.
Yeah, the second act of his life.
Because you would assume a guy who literally built the physical foundation of Silicon Valley would just ride that wave of microscopic precision for the rest of his life.
You'd think so, yeah.
He found his niche. He changed the world. He could easily just keep iterating on manufacturing equipment and call it a day.
And his career does continue in the industry for a while. He didn't just stop with Fairchild.
Okay.
He went on to co-found other major companies. Our sources highlight his role in co-founding Rheem Semiconductor and later a company called Xicor, Inc.
So he stayed pretty deeply involved in tech.
For a time, yes. He stayed involved in pushing the industry forward, refining the manufacturing processes he helped invent.
But eventually, he leaves the semiconductor industry entirely.
He does.
He steps away from the clean rooms and the microscopic precision, and he reinvents himself. And what's wild is he doesn't become a tech consultant. He doesn't become a venture capitalist, which is the standard, well-worn path for successful tech founders in Silicon Valley.
It's almost a cliche at this point.
Totally. But he becomes a visual artist. A sculptor.
And the choice of medium for his art is deeply poetic.
He chose to work in metal.
Yes.
Which is just, he spent decades of his life shaping metal and silicon into these invisible, microscopic, intensely functional circuits. Circuits that you literally need an electron microscope to even see.
Exactly.
And then he pivots to creating large-scale, abstract metal sculptures. It's the exact same fundamental material, right?
Yeah.
But approached from a completely different perspective.
He basically shifted from the microscopic to the monumental.
I love that phrasing.
Because for his entire professional life, his manipulation of metal was governed by the strict, unforgiving laws of physics and commercial utility.
Every millimeter of metal he shaped at Fairchild had to serve a functional electrical purpose, or else it was useless.
Exactly. But as a sculptor, his manipulation of metal was suddenly governed by emotion.
Wow.
By aesthetic expression and human interpretation. He was finally working at a human scale, creating objects meant to be seen and felt, rather than hidden away inside a plastic computer casing.
It is such a profound pivot. It actually reminds me of a microscopic surgeon.
Oh, that's a good
Like
idea.
someone who spends their entire life looking through a high-powered lens, performing intricate cellular level operations,
Yeah.
and then suddenly hanging up their scrubs and deciding to become a large-scale landscape architect, just carving out massive hills and valleys with bulldozers instead of scalpels.
It really is the exact same fundamental manipulation of matter, just flipped from the invisible to the monumental.
Yeah.
And that analogy really highlights the dual nature of his intellect, I think. He understood raw material at its most fundamental atomic level, struggling against its physical limitations to build the early tech industry.
Right.
But he also came to appreciate its potential for broad human expression. And you know what? This pivot from precision engineering to fine art actually mirrors a broader pattern seen among several members of the Traitorous Eight.
Wait, really? You mean he wasn't the only one who stepped away from tech to focus on the arts or humanities?
Not at all. Many of these individuals spent the first halves of their careers intensely focused on the future. They were consumed by securing our technological capabilities and building the raw engines of the digital age.
Okay, that makes sense.
But later in life, after that technological future was secured, many of them turned their attention and their wealth toward culture.
Oh, fascinating.
Yeah, they funded philanthropic endeavors, supported the arts, and in Blank's specific case, physically created fine art himself.
So they built the invisible tools that would define the modern world, and then they stepped back to actively participate in the visible human experience those tools were meant to serve.
I think it demonstrates a profound depth of character. They recognize that technology is a tool for humanity, not an end unto itself.
That's a really important distinction.
Julius Blank passed away in September 2011 at the age of 86. And he left behind a dual legacy that perfectly encapsulates his life.
Which is?
The unseen physical foundation of the digital world operating silently in all of our devices, and the very visible, tangible, abstract sculptures that outlive him in the physical world.
When we pull all of these sources together and synthesize the incredible arc of Julius Blank's life, we are looking at a story that bridges the massive gap between raw imagination and physical reality.
Absolutely.
We start with a mechanical engineering kid born in 1925 in New York City, a guy who finds himself in a room full of theoretical physicists in 97 California, staring at a chalkboard full of math.
A man who looked at the void, the complete absence of the physical tools necessary to build the future, and simply built them from scratch out of raw steel and quartz.
Yeah.
He became the architect of the Silicon Valley factory floor because he understood that a brilliant idea is worthless if you can't actually manufacture it.
And then, after giving the world the ability to manufacture the invisible, he returns to the visible world, finishing his life shaping metal into art.
Because technology is not just math and code. It is forged. It is built by human hands wrestling with the limitations of physical materials.
And that is the core takeaway I want you, the listener, to hold on to today.
No.
Every single time you pull a smartphone out of your pocket, every time you open your laptop, every time you stream a video or load a website, you are relying on a massive, heavy, physical architecture.
An architecture that only exists because one mechanical engineer was willing to roll up his sleeves and figure out how to build the machines that made the machines.
We are literally holding his legacy in our hands.
Really are. And looking back at his story forces us to look differently at the trajectory of technology today.
How do you mean?
The challenges of manufacturing haven't disappeared. They have just evolved.
Which is exactly why I want to leave you with a final provocative thought to mull over. Right now, our news feeds are entirely dominated by bleeding-edge, heavily theoretical tech.
Oh, constantly.
We hear constantly about the dizzying software potential of advanced artificial intelligence. We hear about the mind-bending theoretical possibilities of quantum computing. We hear all about the brilliant new recipes being written. But who are the modern-day Julius Blanks?
The unseen engineers wrestling with the physical constraints of our current era.
Exactly. Who are the mechanical engineers quietly building the physical factory floors right now? Who is designing the massive, hyper-efficient cooling systems required for modern AI server farms?
Because those servers run hot.
They run incredibly hot. Who is engineering the literal nuts, bolts, and thermal housings that will make tomorrow's theoretical breakthroughs an actual reality?
Someone has to.
Because the recipe for the future might be brilliant, but someone, somewhere, still has to figure out how to build the oven.